Okay, well, thank you all for sticking around, and I'd really like to thank Amy for inviting me here. It's been, I think, a decade since I've been back to OCB, and I feel very much at home. I wanted to start off with this disclaimer, right? This is from the source of all wisdom, XKCD. Rachel Stanley assures me that, in fact, the bottom point here, liberal arts majors may be annoying sometimes, but there's nothing more obnoxious than a physicist at first encountering a new subject. Is actually true. So I'm going to try not to be that guy, and I will also, and I do say guy because it usually is one, but also to give you a sense of why you shouldn't be that guy and how not to be that guy. Right? What are the things we need to think about? So the outline of this talk is that, I'm going to start off by talking about allometry in marine ecosystems, drawing on a cautionary tale from fisheries science where the development of actually using allometry is much more mature than it is in ocean biogeochemical cycles, in my opinion. Then talk a little bit about what we know about allometry in phytoplankton and marine ecosystems, and then talk about how we handle it in models. So again, we've already seen this, that a fundamental assumption in ecology is that something like a hummingbird is zipping around and trying to eat substantial fractions of its body weight in one day, whereas a swan is sort of swimming around on the lake and occasionally dipping down and grabbing some watercress. And the rates here are pretty impressive, right? You know, a hummingbird, 2 kilograms of hummingbird is basically generating as much energy as you are. Swans are more or less, are pretty close to the human rate of production. And this has been known for a long time, and there's a long history of modeling this mathematically going back to Pütter in 1920. And all of these models basically have some similar form. You have a variable x, which varies with time. That could be mass, length, or volume. And it has a source term, which varies as some power of that variable, and a sink term, which varies generally as another power of that variable. Now, if we look at this, the time variation at any given trajectory is actually going to depend on 5 parameters. It's going to depend on A, B, and M, X, and the initial value of X. But the equilibrium is much simpler and only depends on the ratio of A and B and the difference of N and M. So it's actually a 2-parameter system in the equilibrium. And that gives you a way of significantly reducing your complexity. So we'll go through a few versions of this equation. The first one is a classic one where the uptake goes as the 2/3 power. The loss goes as the first power. And this is a model that was first proposed by Ludwig von Bertalanffy in 1957 to model the growth of individuals. If one substitutes in here for x the cube of the length scale, then you can do a little bit of math. And what you get is this equation where the length scale varies over time as an exponential. So this basically says that there's an exponential approach to an asymptotic size, right? That's how organisms grow. And it also suggests that the metabolic rate is going to have to go as 1 over that asymptotic size, or 1 over the asymptotic volume to the 1/3 power. So this is where the 1/3 power comes in. The sort of Kleber-West type scalings that Nicholas just talked about can be transformed into exactly the same framework by replacing L cubed with L to the 4th. Then you get exactly the same behavior, right? And you get a 3/4 power rather than, and a 1/4 power law here, right? And the idea being that folding introduces an extra dimension. The fundamental idea there, okay? So the result is that you get this exponential approach towards maximum size, and this just shows a single example I pulled from the literature, and the fisheries community has spent a lot of time constraining such models, and in fact, if you look at the fish-based data set, you can find fits to over to 2,497 as of yesterday, right? So we actually can do this for over 2,000 species of organisms. Just think about how much work that is, right? But what about the sink term? It turns out that there is an alternative way of describing this system. And the is basal metabolism the only thing we actually care about? And the answer is no, because organisms do more than just sit there and exist, right? In fact, particularly for fish, as they get bigger, they devote more and more of their energy to reproduction. And so one could imagine two phases, an initial phase where most of the energy goes to growth, and a secondary phase where more of the energy is going to reproduction. And just from this, you can see that my little model probably fits that data set just as well as an exponential approach to an asymptotic value, right? And it turns out that, and I'll come back to why that's important in a minute. There's a second version of this equation that actually goes back before Pütter. It's the logistic growth equation, which is a classic equation in ecology, where you have, this might be the number of individuals or the mass of, or the biomass, and there you have linear growth, and then you have density-dependent mortality. So the idea is, as I pack more things in, I'm more likely to die because maybe a virus comes through and wipes things out, or I use up my resources. And that kind of density-dependent mortality does seem to actually describe some real fisheries. So this is an example where you have catch per unit effort here and the fish that you get on this axis. And so there is some evidence that actual ecosystem-wide processes can be described by this model. But then you can imagine that we get into particular problems when we try to merge these, right? If we wanted to set a maximum size or a minimum size at which we catch fish, we get rather different behavior if we assume exponential approach to an asymptotic length versus this biphasic growth, right? So in the exponential approach to asymptotic length, these ones are younger and vigorous, and they're growing really fast. These are old and slow. And so if you catch the fish at the top of the curve here, you're just pulling off the ones that are hogging resources and leaving a healthier, more productive ecosystem. And any analogies of this to university academic departments are purely in your own mind. On the other hand, if you have a system in which most of the energy is going to growth here and most of the energy is going to reproduction here, if you set a growth, if you kill off all the fish that in this case are longer than 200 centimeters, you've wiped out all your reproducers, right? It's removing the matriarchs is actually resulting in a disproportionate impact on reproduction. So the lessons I want to leave you from that are allometry can be this immensely powerful tool for data reduction. And it really is a tool for data reduction. But in order to use it properly, you need to understand the actual processes that are producing the growth and the processes that are producing the loss. And that means you actually have to understand the mechanisms that underlie growth and loss. And you need to do that so that you aren't this guy, right? Okay, so continuing. Oop. So now I want to turn to phytoplankton, which we all know and love. What are some of the big patterns that we know about? So one of this that many people in this room have worked on and know far more than me is about the size structure of particulates. This just shows an example of the estimate of the picoplankton fraction of the population versus nanoplankton fraction by Tiho Kostadinov based on work that he did with Dave Siegel for his PhD. And what you see in Tiho's plot here, so that, oops, keep doing that. Sorry. There we go. What you see here is a plot of the percentage of picoplankton going from 0 to 100 and the percentage of nanoplankton going from 0 to 100. And you see what we all know, which is that in the big subtropical gyres, picoplankton dominate, and as you move towards the more productive regions of the North Pacific and North Atlantic, you get a much larger fraction of large plankton. Now we can plot the picoplankton biomass versus the nanoplankton biomass, and when we do, we get this relationship, and this is a cubic relationship here. This is a one-to-one line. Exactly which relationship you get depends a little bit on what seasons you use. So I'm using summertime so that we actually have light and everything's, we're not measuring a lot of dead biomass, hopefully. But there's a lot of structure in here that we ought to be using to constrain our models, and by and large, we do not do that. There are, of course, we do need to understand that there's uncertainties about this. So Frankie Pavia provided me with his own data that he presented earlier in this meeting. Here's the 3-to-1 line. Here's the 1-to-1 line. We've got something in between, although if you look carefully, you might think that there's a 3-to-1 line that transitions to a 1-to-1 line here. And so there's some hints of that in both of these distributions. The exponent may, in fact, be spatially varying. This came up earlier in the questions, that yes, there is evidence for spatial variations. This is from a very nice paper by Jacob Cram that appeared last year in GBC, where he used size structure data from actual UVP measurements and then plotted it against chlorophyll along a particular transect and then mapped it to the world. And you see, again, some large-scale structures that map onto ecosystem structures that we know about. We also know, again, we've known this for 50 years, that productive ecosystems tend to be dominated, have less recycling than ecosystems that are weakly productive, that those ecosystems tend to have more recycling. And so this raises the possibility that we can go between allometry and something like an F ratio, right? That the allometry is, in a sense, is trying to get at this F ratio. And we've tended to implement these ideas in large-scale models with a couple of basic principles. Now, most models have a structure that is generically like the following set of equations. You have a change in phytoplankton, which is growth minus grazing. And so we would write that down like this. The details vary from model to model, but this is a sort of basic structure where you have growth, a growth rate times the biomass, and grazing, which basically depends on some kind of encounter rate between the zooplankton and the phytoplankton. The zooplankton then are governed by some incorporation of this grazing term minus their grazing and loss. And so that has some kind of form like this. Okay. And one of the things that we know on monthly timescales in the global ocean is that the net growth of phytoplankton is relatively small in comparison to the gross productivity, right? So if you get a doubling of your phytoplankton biomass over the course of a month, that's a lot. And yet the phytoplankton that are doing that are doubling almost every day. And so to first order these two terms balance, which means we can cancel the p's and look at, and put the z's to be equivalent. It's less clear that we can do that here, but if we do that, what we end up with is a system where at equilibrium, the zooplankton scale as the growth rate over a grazing rate, and the phytoplankton scale as the growth rate over a grazing rate squared, with some other things to make it dimensionally consistent. So both classes scale as the intrinsic growth rate. So that's the one-to-one relationship. And the way that we then fake the 3-to-1 relationship is by letting small plankton dominate at low nutrients because they have a lower half saturation constant. And so they grow faster than the big ones. And at high concentrations, the large plankton are going to win because they have lower grazing rates than the small plankton. And so this is how those concepts get translated into math that produces the results, right? And all of the models are basically doing something like this. But when you look at what that should produce, this is just one example where we let the large phytoplankton have a half saturation coefficient that's 3 times larger than the small phytoplankton, which is what is done in, for example, I believe both the GFDL model and the NCAR-CESM. You get something that looks like this, where This would be a 1-to-1 slope. This would be a 1-to-3 slope, and you get something that ends up in between. So what do we do? Well, about 10 years ago, Eric Galbraith and I, based on some theory that John Dunn and Rob Armstrong had developed, decided that, well, we would do this by putting this into the model directly. In other words, we would cheat. But it's interesting to think of what that cheating consists of, or what implicitly consists of. Implicitly, what we did was suggest that if the zooplankton mortality were to go as the cube, the grazing rate were to go as the cube of zooplankton concentration, then again, if I cancel disease, what I would find is that the zooplankton cubed would go as phytoplankton. And so the zooplankton would grow more slowly than the phytoplankton for the large phytoplankton. So phytoplankton would go as zooplankton squared, zooplankton go as growth. You end up with phytoplankton going as growth cubed, zooplankton growing as the growth of plankton. Okay. So we encoded that in a model, and you've seen various instantiations of that model over the course of this meeting. So the miniBLING model that was used in the high-resolution ESM 2.5 and ESM 2.6 uses this. And so here's the satellite. BLING is this green line, and the GFDL TOPAZ model, which allows for different growth, different half-saturation constants, is the purple line. And you can see that they all have a somewhat steepish slope. Okay? Granted, we got this because we cheated, right? But I would argue that this model is doing something right that we need to think about whether we can get other models to do right. However, it's not clear it's doing it for the right reasons at all. Now, when we had this model, we didn't have a gridded data set of microzooplankton or mesozooplankton. Thanks to work by Scott Doney and Lowe and others, that we now have this Maridat data set. And the limited information we have there, we can do this a similar scaling. Sorry that this has gotten cut off. This should be nanoplankton concentrations here, and microplankton in red and mesoplankton in black along the vertical axis. And what you see is that the microplankton shows a nice relationship, and the mesoplankton varies all over the place. Though one of the points from going back to my equations is that you get this not by changing the phytoplankton, but by changing the zooplankton loss, right? So, conclusions. I believe we really ought to include allometry as a constraint in our models. And it's a powerful constraint, but we need to be cognizant that the mechanisms by which we can get it differ. Right? We get that allometry by looking at differences between rates, or rate exponents, not the rate exponents themselves. And scaling the grazing with at higher trophic levels may be particularly important. We can produce these different relationships not by playing with the phytoplankton, but by playing with the mortality terms in the zooplankton. If you put a linear mortality term in the zooplankton and that dominates, then what you end up is something that looks like a field where the grass stays at the same level, but if you put more fertilizer on the field, you get fatter cows, right? That's what the mesozooplankton relationship looks like to me. But that's not something that we have tended to think about. We've tended to divide our field up like at the zooplankton grazing, right? At the zooplankton, and not think about how the zooplankton grazing relates all the way down to phytoplankton. Mixotrophy is going to be an additional complication here. And something else to think about is patchiness, because when we're thinking about these grazing laws, we have boxes that are tens of kilometers on a side if we're lucky, and if you're like me and run toy models that only take 45 processors to run for weeks, then your boxes are 300 kilometers on a side. And the idea that the grazing rate is the mean concentration of phytoplankton times the mean concentration of zooplankton over some large box, there's an entire turbulence closure problem that's buried in there that we're ignoring. So I want to leave you with that there's these bunch of questions that are still out there, I think, and that we don't tend to think about because they are just one level above what we think about, but that have the potential to affect the structure in ways that are measurable, and that we need to think about them, but that involves actually listening to the people who know about zooplankton and zooplankton loss and zooplankton grazing, and not being like this guy. So thank you very much.
Allometry from UCI. My question is that when you divide between your nanoplankton and your picoplankton, one thing is like, for example, within the picoplankton, right, you nearly have 2 orders of magnitude differences in size of what you call the same, and the same thing as you're moving up. And secondly, right, there's a variety of sort of trophic strategies even within that one size class. You call them all phytoplankton, but in reality, right, that must be a lot of heterotrophic bacteria. And I see you alluded to it for the mixotrophy as well. So do you think this sort of scaling, like, I mean, to me it seems like it's more like a continuum rather than sort of like these specific classes, and how does that affect this theory? Right,
so I think arguably what one might want to think about is thinking about the theory in terms of a median of a log normal distribution and the spread of that distribution, right? So that those might be the variables that one played with. The fact that there are such regularities there despite all of these things is an interesting point. And I think what it comes down to is something that Nicholas talked about as well, which was that there's still a lot of spread here, right, at a given level. And a lot of that spread is the different strategies and the different, the different strategies, right? But we're still talking about 3 orders of magnitude here that we ought to be able to get, right? So it's what percentage of the variance do those account for? Locally, they may be very, very important. Year to year at a site, they may be very, very important. Across the whole ocean, we still ought to be getting this pattern first, is the argument. Maybe it's not true, but it's the argument.
Hi, Ben Twining, Bigelow, over here.
Hey, Ben.
So I'm struggling with this charge that we need to keep both of these equivalent things in our head, the yes and that we're all leaning into. And so you advocate to use allometry as a constraint, cognizant of the mechanistic sort of details below it. And you talk about how allometry is a data reduction method.
Right.
It seems like we're moving towards a world where maybe we are less bound by the need for data reduction methods as computational ability and measurement ability increase. I mean, I end your talk and I think that it just demonstrates the limitations of allometry, you know, because you point out these, you say, yeah, well, of course we should include it, but, and that's a big but. I don't know, I'm just sort of trying to go back to, Amy, your initial charge to us, and although we see these compelling relationships between size and all these other traits, it seems like they emerge because of, almost happenstance, because of the underlying mechanisms. And I guess my question to you, having just sort of wandered around, is do we really need that data reduction method? And really, should we just continue to struggle to understand the mechanisms that drive these things?
Well, I think part of the answer to that is that this is a pattern that I would argue is important to reproduce, right? How you reproduce it. It's important to I would say it's important, just like it's important to get the pattern of chlorophyll right. But if you do that by simply tuning the chlorophyll to carbon ratio and having the biomass be constant, which you could do in a model, right? You're going to get your productivity just completely wrong. Right? And so that's the basic That's the kind of argument that I'm making. Just simply tuning to a variable, which is easier for us as modelers to do, especially on a global scale, is neglecting, this is a clue to one of the things that we should be looking at. What it is a clue to is something that we need to discuss as a community. That's my argument.
Nailed it. We just hit our coffee break time. Thank you, everyone, for exciting questions, and thank you, speakers so far. We've got more of this after the coffee break. We'll ring the bell.